we'll be looking at the derivatives involving trig functions today. So far we looked at, polynomial type of functions, x to a power, products, quotients, right? These were some examples that we've been dealing with so far. So now we're going to also add to our list of functions the trigonometric functions. Now, as you can see in this section, it is so important to have a good grasp of regular trigonometry before we attend to the calculus with trigonometric functions. So if you feel any weakness in that area, if you feel like you've forgotten a little bit about, what are your basic ratios for sine, cosine? What are your basic identities? For example, tangent function. How can you write that in terms of sine and cosine? Exactly, sine over cosine. For example, your cosecant function. How can you write that? You can write it as 1 over sine. So go over these basic relationships between the 6 trig functions. And also there are very important identities I want to remind everybody about. These identities are going to keep coming up. One of them is sine square x plus cosine square x. What do we know about that? That it's 1. It's one of the most important identities, right? And there are 2 equivalent ones. If you divide everything by sine square, you get 1. If you divide everything by cosine square, you get the other one. Let's remind everybody, one of those is 1 plus tangent square equals, does anybody remember this one? Good, secant square. And the other one states that 1 plus cotangent square equals cosecant square. Good guess. It sounded like you were asking questions, so you had a right guess. So if you know the first, you can really get to the third one by just looking at the second one and just changing to the co-function identity, basically. So these are going to come up a lot. And as always, your trig functions at important angles, such as the unit circle, the 30 degree, 45, 60. If you haven't still memorized those, please take time this weekend. Because if you don't have a strong background in trig, this section is going to feel very, very challenging. But if you have a good background in trigonometry, it should be fine. Okay, I'm going to get rid of all that. Okay, so we're going to begin with the derivative of the sine function. Just to give you an idea about what it is, we're going to begin with a graph. Okay, we're going to actually try to graph the derivative of the sine function. This one I ask that you just simply watch and try to guess what the derivative function looks like. In a minute, I'm going to also show you the analytical way to prove the derivative of the sine function. So let me just try to show you. So I'm going to go to my calculator here. If you like, you can just watch this one because you'll not have to do the same kind of graph in the future. Let's see, where did that go? Okay, I'm going to clear what I have. And what I want to graph is, okay, there is a command under the math menu called the numerical derivative, which is option number 8, and derivative. I'm going to graph the derivative of the sine function, comma x, you always put the variable, and comma at each x value. We wanted to graph the derivative at each x value. Again, don't worry about this. Just all you have to understand is the graph that is about to be drawn is going to be the derivative of the sine function. And see if you can recognize this graph as a function that we already know, okay? And I'm going to go to perhaps zoom trig number 7 to give you a nice graph there. So this is supposed to be the derivative of the sine function that it's graphing. Does it look familiar at all? That looks like a cosine function, right? So just from this initial observation, it looks like the derivative of the sine function. Again, we had this graph just now. The red one is the original function, the sine function. I superimposed it on the same graph. And the other one is the cosine function. So what it gave us was it told us the derivative of the sine function is cosine function, basically. Just as an initial guess. Again, we're going to prove it in more detail in a moment. But let's just check a few things about this to see if it really makes sense, okay? For example, so the red one is the actual function. It's called f of x or y. For example, right here, there's a horizontal tangent for the sine function, correct? So what is the slope right there? The slope right there is 0. So that means the derivative function should have a 0 at that point. And take a look, cosine function, sure enough, it crosses the x-axis. There is 0 at that point, right? Let's check another point. Sine function, it has a horizontal tangent right here, correct? The slope is 0. And check the cosine function. Sure enough, the cosine function has a 0 right there. So these are just a few little things that we're doing to check this. Another thing I can show you is between this tangent line and this tangent line, what is happening to the sine function? It's rising, correct? The sine function is rising. So what kinds of slopes are there on the sine function? Positive or negative? Positive. So slopes are positive. Now look at the graph of the cosine function in that interval between this dot and this dot. You see that cosine function is always positive, right? Slopes are positive, cosine function is always positive. And again, slope is going from 0, increasing, and then again going back to 0. So these ideas give us a little bit more proof, a little bit saying that, okay, this makes sense, the derivative of sine function is cosine function. But if you want to go from scratch, and if you want to say, okay, I want to prove it, I don't want to rely on any graph, what would I do? You would start with the basics, the basic being the definition of the derivative. I'll just quickly run through this again. This part you don't have to write down. But once we have that table filled out, the 6 trig functions and their derivatives, I'm going to ask you to write that down, and I'm going to ask you to memorize those, because those are going to come up over and over. But once again, how do we get the derivative of sine function? How would you apply the definition of derivatives with this? F of x plus h, what would that be for the sine function? Sine of x plus h, right, minus f of x, which is minus sine of x, everything divided by what? H, and the limit as h goes to 0. So we applied the definition of derivatives. Now, do you guys learn about some formulas in trigonometry, like sine of a plus b kind of formulas? Does anybody remember seeing things like that? Deep down in trigonometry, you do like sine of a plus b, cosine of a plus b. There are formulas for those, right? So if you expand sine of a plus b, using those formulas, in this case x and h, you get sine x cosine h plus cosine x sine h. That's a formula from Trig. And we still have the minus sine x. Then we're going to collect this term with this term, because they both have a sine x in them. And I will factor out the sine x from those two. So what would I have left if I factor out the sine x? Cosine h from here and minus 1 from here. That's what I have. I factored out the sine x. I have cosine h minus 1. And then the second part, I'm writing exactly as it is. This middle part, cosine x times sine h over h. You see, I wrote it exactly as it is. And I distributed my limit sign over a sum or difference here. So I put it as 2 limits. You can't do that with limits. And finally, what do we know about this limit? Sine h over h as h goes to 0. That limit is 1, right? So if you look at my second part in here, okay, what you have is cosine x, which doesn't depend on h, so you write it exactly as it is. And the other part is 1. So this part is going to be cosine x times 1. In this initial part, I have to tell you that this limit turns out to be 0. Sine x times 0 turns out to be 0. So finally, if you put every pieces together, you end up with 0 plus cosine x times 1. In other words, you end up with just cosine x. So that's the derivative of sine with cosine. So it was so much easier to understand when you just look at a graph. But a real mathematician, you know, if anybody pursues further in math, like a math major, or they would never be satisfied by just looking at a graph. They want to know solid proof based on identities, based on equations, and this would provide that kind of proof, solid proof for them. So we're going to go back now and write in our chart that derivative of sine is cosine x. I want you to memorize that. We're going to use it over and over again in this class. Okay. So I'm going to fill this table today together with you guys. So the first one we found out is that derivative of sine is cosine. That's the first thing that we have observed this morning. And the other one, let me just tell you right now, you can do similar thing for the cosine function. The derivative of cosine turns out to be negative times sine x. And by just knowing these two derivatives, you can actually fill in the rest of these values by applying the rules we learned from last time. For instance, tangent x. If I want a derivative of tangent x, let's first write tangent in terms of sines and cosines. What is tangent? Exactly. So let's write it that way. So to find the derivative of tangent function, first rewrite the tangent function as sine over cosine x. Eli, any questions? Any comments? So we're going to find the derivative of sine over cosine. What rule should I use to differentiate this? How about the quotient rule, right? So according to the quotient rule, we write down the lower expression as it is, cosine x, lower times the derivative of the higher. We just learned what is the derivative of sine? Is cosine. Do I have a plus or minus in the middle? Minus for the quotient rule. Now the higher term, which is sine x, times the derivative of the lower, which is derivative of cosine, that is negative sine x. Everything should be divided by denominator squared. In this case, that's cosine square x. On the top, the two negatives, the negative sign will give us a plus in the middle, right? So we're going to have cosine square plus sine square on the top, right? And how can we simplify that? As 1. So what is the final answer then? So 1 over cosine square x, and very good. You can simplify 1 over cosine square as secant square x. So this is the result I'm going to fill in our table, that derivative of tangent is secant square. And again, this is one of the 6 that you have to memorize. It's going to come up from now till the end of the calculus sequence and beyond if you're an engineering major. So make sure that you are familiar with the derivative of the tangent function as well. How about the secant function? Let's find out the derivative of the secant function. We'll apply the same little trick. Write secant in terms of sines and cosines. In this case, secant is the same as 1 over cosine. Now let's apply the quotient rule to 1 over cosine x. And Ryan, help me out here, okay? Yes. So we're going to start with the quotient rule, right? So we want the lower term first, times the derivative of the top, which will be 0, right? Minus the higher term, which is 1, times the derivative of the lower, which we just learned, is negative sine x. Everything divided by the bottom squared, which is indeed cosine square of x. Now, if we simplify this a little bit, we have sine, positive sine, because 0 times anything is 0, right? You have positive sine over cosine square. But usually, you're not going to see in the textbooks as this being the answer. They simplify this a little bit differently. They write it like the following. They say, this is the same as 1 over cosine of x times sine x over cosine x. First of all, would you agree that this expression can be written like the second part of the equality? Yes, we just split the cosines as cosine times cosine instead of cosine square. Now, what is another name for 1 over cosine x? That's secant, right? And what's another name for sine over cosine? That's tangent. So usually that's the format in which you're going to see the answer, which is secant times tangent x. So what we have determined then is, let's put that up in the chart, the derivative of the secant function is secant times tangent. Exactly. Interestingly enough, secant function shows up in its own derivative. It's still there, but it's multiplied by the tangent function. Now I'm going to show you a quick way to get the other ones without doing any work. Basically, if you know the derivative of a trig function, the derivative of the cofunction is going to be negative 1 times the cofunction of the derivative. For example, if you knew the derivative of sine was cosine, to get the derivative of cosine, you look at that right-hand side. Instead of cosine, you make it a negative and switch it to its cofunction, make it a sine. So for example, if you know the derivative of tangent is secant square, let's take a guess as to what do you think will be the derivative of cotangent. First, there's going to be a negative involved. And instead of secant square, guess what we're going to have? What is the cofunction of secant? Cosecant, so we're going to have negative cosecant square of x. Now let me have you try to guess this one. We already know derivative of the secant function, right? Secant function has a derivative secant tangent. Now we want a cosecant derivative for the cosecant function. Okay, I heard a good suggestion, but let me hear the same suggestion from another student, if I may. So I'm looking. So we're going to use the following. We know that derivative of secant is secant times tangent, correct? Now I want the derivative of cosecant. So all I have to do is negative cofunction, right? Put a negative. What is the cofunction of secant? Cosecant. What is the cofunction of tangent? Cotangent. Therefore, the derivative of cosecant is negative cosecant times cotangent. So these 6 identities, just that we came up with, these 6 rules are going to keep coming up. So I'm going to box them in and just ask you to memorize them. It's very, very important to memorize them early on. As a matter of fact, what I'm going to do is I'm going to give you a few moments right now. I'm going to stop the recording, give you some time to look at this and try to memorize it. I'm going to be asking you in just a little bit. And if you're online at home, please pause the recording yourself. As we do the examples, you will see these will come up very often. So let's now do some examples. Just look at one at a time. Okay, starting with the derivative of 6x squared minus sine x. Now, all the rules that we have learned in the last section still do apply. For instance, if you have a sum of 2 things, go one piece at a time. If you have a product of expressions that involve the variable, then apply the product rule. If you have a ratio of things, apply the quotient rule. All those rules apply, but now we're also throwing in some extra, some trigonometric functions, as you can see. Okay, so here we have f prime of x equals. So we're going to go piece by piece. Derivative of the first piece, 12x. Derivative of the second piece, it's cosine, but the minus in the middle has to stay, so it's going to be minus cosine x. Okay, how about this one? X times cosine. Let's find the derivative of this function. Give you a few moments. Do we need to use the product rule here? We do, because you have x times cosine x. Both of these are functions of x. If you had like 5 times cosine x, that's the constant multiple rule. There you don't need the product rule. But if you have 2 things being multiplied and both of which contain the variable, we need to apply the product rule. So that's what we're going to do here. F prime of x equals. So again, you could say the derivative of the first, which is 1, times the second, plus the first expression times the derivative of the second, which is negative sine x. You could do it a number of ways. Because remember, because there's a plus sign in the middle, it doesn't matter which order you write. So you could have also done like this. X times derivative of cosine plus cosine times derivative of x. So that would give us the same answer. Then is there a way to simplify this? All I can do is really just put the minus in the middle, so I can say this is the same as cosine x minus x sine x. But the important thing here was to remember to use the product rule. Now, what if I have 7 times cosine x? What is the derivative of 7 times cosine x? Let me write it here. So y prime would be negative 7 times sine x. In that case, you have a constant multiple. Just like we learned in the last section, if you have a constant multiple, you don't really need to apply the product rule. Although you could apply the product rule, but one part is going to be 0, it's going to drop out, you get the same answer, but there is no need, basically. Okay? All right. Pardon me? Yes, for that question, you can leave it just like that. Okay, how about this example? And before we look at that example, any questions about the first two? Yes, Daniel?
So, like, multiply the x by the negative sine x.
For this question?
No,
for number 2, over here I just simplified because x times negative sine x can be written as negative x times sine x. I just simplified it that way. Exactly. I just pulled the negative out, basically. Yes. Okay, here you have another one to work on. This time I'm going to give you some time to think about cosine x over 1 plus sine x. And please make sure you simplify your answer as much as possible. So with the quotient rule, let's see, f prime equals. So I take the lower expression times the derivative of the higher. We just learned that one, right? So that's negative sine x minus the higher expression times the derivative of the lower. What is the derivative of 1 plus sine x? Just cosine it, because the derivative of 1 is 0. So it's going to be just cosine x. Everything over the bottom, quantity squared. Now all we need to do is simplify the numerator. Let's distribute that negative sine x into both of those two terms. So negative sine times 1 is negative sine. And negative sine times 1 is negative sine. Negative sine times sine is negative sine squared. And the last two multiplied together gives me negative cosine squared or minus cosine squared over the same denominator. Okay, here we should see a famous identity appearing in a different form. What is that famous identity? I'm thinking of sine squared plus cosine squared is 1. Therefore, negative 1 times that. In other words, negative sine squared minus cosine squared is equal to negative 1, right? Because again, we know sine squared plus cosine squared is 1. So if you were to factor out a negative 1 from that quantity, you're going to have negative 1 times sine squared plus cosine squared in parentheses. So that numerator then can be rewritten as negative sine x and then what? Minus 1. Okay, it looks like we might be able to do one more thing here. Factor out a negative from the top. So if we factor out a negative from the top, we will have negative 1 times sine x plus 1, or I'm going to write it like this, 1 plus sine x, same thing, right? All over quantity 1 plus sine x squared. Can I simplify anything here? Basically, on the bottom here, 1 plus sine x multiplied by 1 plus sine x, right? That can be taken away with one of the ones on the bottom with the one on the top. So we are left with negative 1 divided by 1 plus sine x at the bottom. Okay. The next one should be a lot more straightforward. No quotient rules needed there. Let's take a look at that one. So direct application of those, knowing your trig identities for this one. No fancy things. Okay, did we all get this result? Derivative of tangent is secant squared, right? And derivative of secant is secant times tangent. And because it's constant multiple, those multiples remain there. Did everybody get the same thing? Any questions about that one? Because it's a sum, I really, you could technically factor out a secant if you wanted to, but that's pretty much as far as we can go. Let's just take out a secant of t. What is left then behind? 5 secant t from the first plus 3 tangent t from the other. Pardon me? That is the derivative, yes. Okay, here's another example. Let's just look at the top one to begin with. For this question, I'm going to give you a hint. There are two ways to do the problem. One way is going to be easier. And the easier way is, if you first multiply out the cosine, and then if you can try to simplify things, like maybe rewrite cosecant in terms of its equivalent. If you simplify before you even begin, it's going to be much easier. If I have time, I'm going to show you both ways how to do this problem. But multiplying it out first is the easiest way. So I'll simplify it first by multiplying it out. Now, cosine times cosecant. I'm going to rewrite. Cosecant is the same as 1 over sine. So I end up with cosine over sine there, right, on the second term, which is further simplified as what? Cotangent. I haven't done any differentiation rate yet, just simplification, right? Now we're ready to differentiate this. Okay, so differentiate the first term, negative sine x, and differentiate the second term. If you remember derivative of secant, if you know the derivative of tangent, go from there to find the derivative of cotangent. Good, negative cosecant square x. So try this later. If I have time at the end, I'll come back, but I think today I'm running out of time. Try this. Apply the product rule to this question and see if you can get the same exact answer. Okay, so just put it as a homework or an exploration problem. Applying the product rule is a really good exercise. You will get the same answer, but it's going to take a lot more work. It's a good exercise in trig, simplification, and identity, so I would recommend you do that. Because you see, when you multiply it out as the first step, we ended up with this. So we didn't apply the product rule here, right? But if you apply the product rule, how are you going to proceed? You're going to say, okay, this is my first term, f of x. This is my g of x. So fg prime plus gf prime. That would be the way to do it with the product rule, okay? All right, but for now, I want to give you one more example. Would you please also look at this number 6? Differentiate tangent x over 1 plus tangent x. Once again, leave your answer in the most simple way possible. Okay, once again, the quotient rule, right? So the lower expression times the derivative of the higher minus the higher expression. Okay, what will be the derivative of the lower one? Derivative of 1 is 0, right? Derivative of tangent is secant square x all over the denominator squared. Okay, now we can distribute the secant square over here as secant square x plus secant square times tangent minus secant square times tangent at the end there. So clearly those last two terms are going to cancel, right? But I still have the bottom there. One plus tangent x quantity squared. So all we have left then is on the top is secant square x, and on the bottom 1 plus tangent x quantity square. Now this might be tempting to do another cancellation here, but can we really do it? Not really, right? Because the bottom one, if you were to expand it out, it's going to be 1 plus 2 times 1 and tangent, so 2 tangent t plus tangent square. So that there's more there, and then there's terms. You really cannot simplify it. You may want to try it, but it doesn't work out. So you say, okay, this is as far as we can go for this question, and we're going to leave the answer like that. Okay? In the last 10 minutes, we're going to do a group activity. All right, let's also take a look at this question. To find the equation of the tangent line to the given function y equals tangent x at the given point x equals to pi over 4. So to find the equation of a tangent line, we need to know a few things. We need to know what the slope is, the slope of the tangent line, and we need to know a pair of points that this line goes through, as in x sub 1 and y sub 1. Basically, we just know that ordered pair x sub 1, y sub 1, and the slope, we can write the equation of this line. Let's begin with the slope. So how do we find slope of the tangent line? We need to find the derivative, right? So let's find the derivative of the tangent function, which is, as we learned today, is secant square of x. We want to find the slope at the point pi over 4. So we need to calculate secant square of pi over 4. Now to evaluate this, I would suggest that we think of the cosine function first. What do we know about the cosine of pi over 4? You could say root 2 over 2, right? Or the same thing can also be written as 1 over the square root of 2, same thing. So the secant function at that point is going to be the reciprocal, which is root 2 over 1 or root 2. But we want the square of this. If you square it, you're going to get 2. So that is the slope at that point. To get the y-coordinate, we need to plug pi over 4 into the original function. So y equals tangent of pi over 4. And pi over 4, of course, is 45 degrees. Sine and cosine are equal at that point, and their ratio equals 1. So tangent pi over 4 equals 1. So now we have everything we need. The point is pi over 4 comma 1, and the slope is 2. So now we're supposed to write the equation of a line with that information. So to do that, we just put it in the point slope form of the equation of a line. Y minus 1 equals slope times x minus pi over 4. And multiplying this through, 2 pi over 4 can be simplified as pi over 2. And adding the 1 from the other side, we get the following. You could simplify it just a little bit. Leaving it like this is fine, but you could also write this as, because less plus 1 is 2 over 2, you could also write this as, and put it as a single denominator. I'm going to put it as 2 minus pi on the top. You could put negative pi plus 2 on the top, same thing, over 2. So this is an optional way to leave it, but leaving it this way would be perfectly fine as well. Okay, one more thing I'd like to do as the last activity for today's lesson, and that is checking something we did from the earlier part of the lesson. Remember this example, cosine x plus 1 plus cosecant, and we first simplified and then we differentiated it. This time, I'm going to use the product rule. Let me open a new space for that. Okay, so we're going to do the same example with the product rule, and we'll go back and check our answer. if you see more than one way to do a question in this section, when you're doing the homework, I suggest you take both paths, both approaches. The reason being, you're going to get more practice on simplifying trigonometric expressions and also more practice on working with derivatives of trig functions. And at the end, trying to show that answers are the same from both approaches. You will really work your trigonometric muscles here really well if you do that. Okay, so we're going to do with the product rule right now. So with the product rule, okay, what I'm going to do this time is I'm going to write down the first function exactly as it is and multiply it by the derivative of the other function. So this is my first function, and this is the second function. Derivative of cosecant is negative cosecant times cotangent plus, so far I have the first times derivative of the second. Now I'm going to write down the second one as it is, and times derivative of the first, which is negative sine. Of course, you could have done this in the other order. Since there's a plus sign in the middle, it doesn't matter which one you differentiate first. Just you have the derivative of one times the other, and then you swap them around. Okay, so now we're going to simplify this. Let me write everything in terms of sines and cosines. Okay, cosecant is 1 over sine x. Cotangent is cosine over sine x. And distributing the negative sine x, we get minus sine x. And then negative sine times cosecant. Remember that cosecant is the same as 1 over sine. So it's as if you're multiplying 1 over sine with negative sine. And what will the end result be? Negative sine x times 1 over sine x. That end result would be negative 1, right? Okay, if we simplify this, multiplying these together, on the top I have negative cosine times cosine, or negative cosine square x, and on the bottom sine square x minus sine x minus 1. And the cosine over sine, of course, is cotangent, and because I have a negative, it will be negative cotangent square x. And let me put the minus 1 next to it and negative sine x afterwards. I will group these together because there is an identity that I can use. If you were to factor out a negative 1 out of these two, you would have 1 plus cotangent square, and that was the famous identity cosecant square. But because there's a negative on both, it's going to be negative cosecant square minus sine x. Now let's go back and check the answer from the last version of the solution, which is the same thing. Just the order, of course, doesn't matter since they're both negative. Negative cosecant square x minus sine x. Same answer, and same answer we got either way. Of course, the first way was much easier. As a general rule of thumb, if you can simplify something before you even begin, usually that's going to be easier. But if not, you can more than likely still get the same answer. It might just be a little bit extra work. So that concludes our lesson on derivatives of trigonometric functions.